In this video, I would like to discuss the multivariable chain rule with you. What I would like to do is present the chain rule, talk through why it is the way it is, and then we will do a few examples and kind of see how you often encounter the chain rule in practice. In a separate video, which I will link to, I will do the proof. So I'll save that for a different video. I would like to open with this question. Why is matrix multiplication defined the way it is? So if you're a student of mathematics, you should know the answer to this question. Let me just kind of imagine the day you first learned about matrices. I think I was like 10 or 8 or 14. I don't really remember, but I was a child in school, and matrices were just presented to me as grids of numbers. There wasn't a lot of context for what matrices do, why they are important. I was told, okay, if you have two matrices and they're the same size, to add these two matrices together, you just pair up the components and add them. Makes sense? Not sure why we would do that, but it makes sense algebraically. Then if you take a matrix and you want to multiply it by a number, that just amounts to distributing the number to each of the coordinates. Again, why would we do this? I don't know, but it makes sense. I can do this. So then you move on to matrix multiplication, and you probably expected it, like I did, to be just like matrix addition. You just pairwise multiply terms, and that's not the case. Instead, we have this really mysterious algorithm where I always do this with my fingers, but you go across one row and down one column, and you do this whole big action just to get to one term at a time. Therefore, your inner dimensions need to match. And again, it was unmotivated. And I also had no idea for the longest time why it was defined that way when there seems to be a much easier way to define a matrix product, right? So why do we do it this complicated way? So pause. Some of you probably know the answer immediately. Some of you might come to it, but give yourself a few minutes to think through this question, and I will come back and explain it to you here before we move on to the chain rule. Understanding what a matrix product is communicating is really the fundamental idea behind the chain rule. So I want you, whenever you think about a matrix, to realize that to that matrix, we associate a linear transformation. That's kind of the backwards viewpoint. Normally, we say, imagine you have a linear transformation. Say T sub A is a linear transformation taking us from Rn to Rm. To this linear transformation, we associate an M by N matrix. I'll call this A to match my subscript here, so that T of X, where X is a vector in Rn, can be computed by doing this matrix product, the matrix A times the vector X. Let me give you a second linear transformation. We'll name it T sub B. And I'm going to set this up so that the domain of the second linear transformation is the codomain of the first one. So this is a linear transformation taking us from Rm to Rq. Again, since this is a linear transformation, to this transformation, we associate a Q by M matrix so that, let me call this Y. T sub B acting on the vector Y in Rm can be computed by doing the product B, the matrix B times Y. Just a side note here, all my computations and analysis too in this context are with respect to the standard basis coordinates, in case you're wondering. All right, the way I've set this up, we can compose these two maps. So if I do T sub B of T sub A, what that's going to do is start us in Rn, map us to Rm through the action of the first one, and then map us to Rq through the action of the second one. So that overall, as a function in its own right, this composition is a map from Rn to Rq. We can say more about it, though, because we know how each of these pieces acts individually. In particular, what does it look like to do this computation on, say, a vector from Rn? So let me go ahead and write T sub B acting on Ta of x. So my inside function is this first linear transformation. We know what this is explicitly. It's A times x. So this is now the linear transformation T sub B acting on A sub x, which is a vector in Rm. So I know how to act on that vector. I'm going to take this and multiply it from the left by the matrix B. Now, this matrix product that we create when we, say, first invented how to multiply matrices should be associative. That is a property we do not like to lose with multiplication. So this is like BA, that matrix, acting on X. And I'll leave it to you to check that the dimensions of this matrix product should be Q by N. All right, so that's really why matrix multiplication is defined the way it is, this strange process that I still use my fingers for, even though I've been doing it for years. That algorithm encodes how the composition of the two individual transformations must behave. So the way that we define this product matches the action of first doing T sub A and then doing T sub B. This also illustrates, once you realize this viewpoint, that to the matrix product, we can think about individual linear transformations and then composing them. That illustrates why matrix multiplication is not commutative. So that's something that's also very surprising when you're a child, because multiplying numbers is commutative, but multiplying matrices usually is not. And that is because if you take two functions and you can perhaps compose them differently. So imagine that both of these maps are from just Rn to Rn so that I could compose them in either order. The action of one followed by the other is not necessarily the same as doing it in the reverse order. I think what I would like to do is step aside for just a moment, and I will put up a MATLAB demo where I take a vector in R2, and I imagine two very famous linear transformations acting on the xy plane. So one of them, say T sub A, will be the action of rotating vectors by pi over 6. And then T sub B will be the linear transformation of reflecting over the x-axis. So I'll just put this up here, and you will see that multiplying, let's say doing the product B times A like this is rotating and then reflecting. That is not the same thing as A times B, which would be reflecting and then rotating. Okay, so sorry, I've just dropped my marker, so I'll pick that up, put up the MATLAB demo, and then when I come back, we will talk about the chain rule, because it feels like we've gotten a little off topic, but I promise that we haven't, because again, understanding why matrix multiplication is the way it is, what it's actually doing, tells us a lot about the chain rule. All right, so here's the statement of the chain rule. I have this kind of preamble at the top, and then I'll continue it down here. The three lines at the top are really just telling you that the composition makes sense dimensionally, and also our functions that we're going to compose are differentiable where we're about to assess them. So since it's a big statement at the top, I'll give you a moment to read through that. But again, just keep in mind that we're trying to say that the composition that I'm creating out of the functions f and g takes us from some open domain in Rn to some subset of Rm to Rq. So here, this map is through F and this map is through G, so that G of F takes us from Rn to Rq overall. Okay, so just take a moment to read through this. Again, it's just telling us the composition is nicely behaved, and then I will state the heart of the chain rule, which is how do we compute the Jacobian matrix for H, assuming that H is even differentiable. That's part of the result. So the heart or the conclusion of the chain rule is actually down here. If I have a composition like this, where I'm at a point P in the domain where F is differentiable, and also G is differentiable at F of P, then the composition as a map from Rn to Rq is also differentiable at P. So that is something that we need to verify, that the composition is itself also differentiable. And the Jacobian matrix for the composition at P is a matrix product. So I'll state this like the single variable calculus chain rule. So I'm going to say out loud the words I usually say when I'm doing single variable calculus, and that is derivative of the outside evaluated at the inside times the derivative of the inside. So it mirrors the perhaps more familiar chain rule. Think about what this is saying. It's saying that the linear transformation that we want to associate to the composition is the composition of the individual linear transformations. So the Jacobian of a composition is the composition of Jacobians. What do I mean by composition here? It's a matrix product. So a matrix product is representing a composition of linear transformations, and that's what we have here. All right, in a separate video, I will prove this, and it's really going to mean proving two statements. One, that the composition is actually differentiable. That's a statement in its own right. And then also that it's differentiable, and this is the linear transformation, which gives us the good first order approximation for our function centered at P. What I would like to do now is take this statement, this idea that the Jacobian of a composition is the composition of Jacobians, and I want to look at a few examples. So I will present like a very common statement of the chain rule in multivariable calculus that we often just teach and we don't really say where it comes from. So I'd like to show you where a sort of famous set of equations comes from. We'll do a sample computation, etc. So I hope that the rest of this video just shows you how to like use this product. Let's look at this common context for the chain rule. I've set it up as a composition here, but I'm actually going to present it to you a little bit differently in just a moment. So what we're going to imagine is that we have a map from R2 to R3. So here, using the language of the chain rule I just expressed, that could be your function f. And then from R3, we take these coordinates and plug it into some scalar valued function g, which is a map from R3 to R. So it's like g of f is the composition that we're looking at here. What I actually am trying to describe with this composition is the idea that this function g, which is scalar valued, depends on, say, three coordinates, u, v, and w. So g is a function of three coordinates. But now imagine that the coordinates I want to evaluate g on each individually depends on, say, x and y. So this is like this kind of composition presented as a tree. Since g depends on u and u depends on x and g depends on v and v depends on x, etc., g depends on x. So how can we think of how g depends on x, what you might write as dg dx? Let me actually first give you the formula that we often just give in multivariable calculus, and we don't necessarily say where it comes from. At least that's not the tradition that I've seen. How we often present this dependence that g has on this lower level is we'll say dg dx is dg du dx. Trying to do fancy d there, du dx plus dg dv dv dx plus dg dw dw dx, and I am shocked I didn't make any mistakes here. I almost always write at least one letter wrong, but I don't see anything. And then likewise, how does g depend on y? I'll just say this out loud. dg dy would be dg du du dy plus dg dv dv dy plus dg dw dw dy. So if you're a student and you're looking at this, it's kind of a strange expression. It's like, where did this come from? Why is it these three products added together? These are not fractions. They are rates of change. So you can't actually cancel out the DUs and the DVs and the DWs, but when you're a student, you kind of mentally imagine that you do. And what you would end up with is something that's kind of like 3 dg/dx on the right-hand side. So where does this formula even come from? Okay, A, you can't just cancel out, like I just said. And B, I encourage you, whenever you're looking at a statement like this, and you're trying to figure out what led to this statement, if it is a sum of products, then it might have been the result of a dot product or a matrix product. So here it's like I've got pairs added together. Those pairings actually came from a matrix product. Here's how I will now verify that with the chain rule. Typically, we do write this as dg dx, where we're saying how does g depend on this x coordinate down here, and this is the expression. Because I've phrased this composition using the language of the chain rule, I'm going to switch now to thinking of this composition starting all the way here and ending here as h. So h is g of f. Let me write that out. Set h to be g of f. H ultimately in this presentation is a map from R2 to R because G is scalar valued, which means its Jacobian matrix is 1 by 2. In fact, we can say what the coordinates would be. They would be dH, dx, and dH, dy. Okay, so this is the Jacobian matrix for the composition. It's 1 by 2. And now I want to write this as the product of two other matrices. Take a moment just to see if you can do this on your own using the chain rule that we just looked at. You can check yourself before I come back. If you do the product of the two matrices you get here, one of the lines should look just like this computation, and the other one should look like the one I did out loud with y. Okay, the first matrix is going to be the derivative of the outside. So that's the section of G here. G is a map from R3 to R, so this is going to be a 1 by 3 matrix. And it's just given by dg du, dg dv, and dg dw. I'm actually going to say a little bit more about this in a moment, but let's just keep going with our matrix product. So this is the first one. The second one is differentiating this map here. This is from R2 to R3, so that's going to be a 3 by 2 Jacobian matrix, so 3 rows, 2 columns. And it's the coordinate functions here are u, v, and w, and they are functions of x and y. So the first row of this matrix is going to be the partial derivatives of u with respect to x and y, then v with respect to x and y, then w with respect to x and y. It's more to write down, so I'm going to use subscript notation. So du dx, du dy, dv dx, dv dy, dw dx, dw dy, and I still think I don't have any typos, which is great. Okay, so this is 1 by 3. This is 3 by 2, returning us our 1 by 2 matrix. And if we were to actually compute this now with our fingers, we would get dg du du dx, that's here, plus dg dv dv dx, plus dg dw dw dx. Oh, I did have a typo. I told you, I almost always write at least one of these wrong. Yeah, okay, so I think that's the only typo so far. Dg dw dw dy. No, dx. Okay, I got turned around. But anyway, so this row with this column gives us the dependence of g on x. And then this row with this column gives us the one I did out loud. So dg du du dy plus dg dv dv dy plus dg dw dw dy. Let me say a little bit more about what's going on here. So this is dg. When you do the chain rule, the derivative of the outside evaluated at the inside means that basically you want to evaluate it on the coordinates that get plugged into that map. So that is u, v, and w here. And then this is df, x, and y. Okay, so that's the matrix product that we have here. Again, I've named this composition H so that after doing these products, the two terms that result are dH dx and dH dy. But as I said when I first wrote this formula out, often this is presented to students as the dependence of g on x, because g, this kind of top-level function here, does depend on x through u, v, and w. So this discrepancy in the notation there just reflects the two different ways that this material is presented. All right, let me step aside, and then when I come back, we will look at another common application. This is the other context that I would like to look at in detail with the chain rule, and I'm going to talk about this in generality first, then we will look at a specific example. Before I write down the chain rule for this composition, I want you to take a moment to look through this composition, realize what kind of functions these are, and then think about why this composition is important. Why am I highlighting this particular type of composition? So pause and see if you can give some meaning or story to this type of composition before I come back, give you my point of view, and then we'll just write down the chain rule for this composition. Breaking this up piece by piece, what we have here first is a vector valued function on scalars. So t is a scalar. This little vector symbol I put over my r is trying to indicate that the output here for this first map is a vector. We're talking about a chain rule, so we're assuming that where we're about to assess differentiability, everything here is differentiable. If r is at least continuous on its domain, then this vector valued function of the scalar is a curve. I could have maybe spelled out some hypotheses a little bit more to indicate that, but what I want you to see is that, if you have this kind of parameter, like we're parametrizing with respect to time, and we're being sent to R2 or R3, typically that's indicating a curve. So if we're assuming that our function is at least continuous on the domain, what we would have is, if the outputs are in R3, some kind of space curve. Okay, so this first mapping is a curve, and then we have a vector valued function on that curve. So f here, if we stick with our picture, f may be a function in general from R3 to R, but what we are interested in is evaluating f along this curve. Perhaps my curve is in this room and f is measuring temperature. So I'm saying, well, how does the temperature change as we move along this curve? So that is what this kind of composition, it starts with scalars, goes to some kind of Euclidean space, R2 for a plane curve, R3 for a space curve, and then sends us back to scalars. Think of that as evaluating some scalar quantity along a curve. For the chain rule, all I want to point out before we look at the example is that for this particular context, which comes up all the time, because again, we could be interested in pressure along this curve or temperature along this curve. The idea of measuring a quantity along a path is something that you do in science. Because of that, we have special notation here. So I'll write down the general statement of the chain rule, and then I'll translate it into more specific symbols, basically, that are intended to communicate to the reader the exact geometry of the situation. So just to state the chain rule without thinking about the context, we would say that the Jacobian, how do I want to phrase this, like that? Yeah, let's do that. At some time t where this composition is, say, differentiable, the associated Jacobian is going to be df at the point on the curve in question, so df evaluated at wherever we are interested in, times dr at that moment in time. This is not incorrect. This is the chain rule. So the derivative of the composition is the composition of the individual Jacobian matrices. But scalar valued functions are special. Curves are special. So there's a type of notation you can use in this context, which again, when you see it, I think it just communicates like a better sense of the picture of what's going on. If you see this, you just think, oh, general Jacobian matrices, and maybe you lose sight of the geometry of the situation. Since f is scalar valued, let's say this is Rn, this is a 1 by n matrix, and this is n by 1. So we've got a row matrix times a vector. The result is actually a scalar. So that's neat. The Jacobian matrix is actually just a 1 by 1 scalar, and that makes sense because overall, we're starting with a scalar and we're ending with a scalar. So the composition, if you kind of took out this middle step and you just looked at the end result, it's going to look like a function from R to R, just like y equals f of x. So that's one thing to note. The other is this is a row. Multiplying a row times a column gives you the same result as if you took this row, flipped it into a column, and did the vector dot product. It's the same sum of pairwise products. So I'm going to recognize that if I flip this row into a column, it has a special name. It's the gradient of f. I'm going from classic matrix multiplication to a dot product when I do that transpose action for this first product here. And then just like there's a special name for this, the derivative, this Jacobian along this curve, it's a vector. If you actually figure out what it looks like, it's going to be this tangent velocity vector. So this is what we often call r prime of t. So the derivative of this composition is the dot product of the gradient of the scalar valued function and the velocity vector along the curve. And when you see this, I think it just communicates more about what this kind of composition is computing. So just to explain again what this change was, this is now an n by 1 vector, and this is a vector as it was before. And then this is a dot product. Both this row times column and the dot product of these two vectors will give you the same scalar. So that's the little change I made here to go from general language to something much more specific. Okay, I'm going to step aside, and when I come back, we will stick with this context, and I'll just give you an example, kind of showing you a curve and a function. And if we want to measure the rate of change of our measurement along this curve, then we will use the chain rule, kind of save ourselves from having to actually do the composition. Let's use the chain rule effectively for this example. So here we have the curve. R of t is cosine of t, sine of t, t squared. I didn't give a domain for the parameter t, but you can imagine that t goes from negative infinity to infinity. And then our scalar valued function of three variables is f of x, y, and z is x cubed plus y cubed minus cosine of x times z. We want to imagine that we are measuring our function along the curve, and we want to know the rate of change of the function just restricted to the curve. I've given us two specific moments to think about, so we'll start with t equals 0, then I will give you a chance to work through t equals pi before I finish this lesson with that example. Okay, let me jump straight to the vector dot product where we left off a moment ago. If I want to know the rate of change of f along r at the moment when t equals 0, what I want to compute is the dot product of the gradient of f at r of 0 dotted with the velocity vector at 0. So let's see, we need r of 0, we need the gradient, we'll evaluate it at r of 0, and we need the velocity vector. Okay, so let's do the gradient of f in general. It's going to be 3x squared plus z sine of xz, 3y squared, and then x sine of xz. If I started plugging the coordinates for my curve into this expression, that would be a mess. What would that look like? X would be cosine of t, y would be sine of t, and z would be t squared. I don't need the gradient of f along the entire curve, though. I only need it at the point where r of 0 occurs. So what is this point in R3? Let's evaluate r of 0. Cosine of 0 is 1, sine of 0 is 0, 0 squared is 0. So I just need the gradient here. Okay, so let's do that. Let's see, 3 times 1 squared is 3 plus 0, so 3. And then 3 times 0 squared is 0. And then 1 times sine of 0 is 0. Okay, so we get 3, 0, 0. Much simpler than either plugging in here or even going back to the original functions and plugging the coordinates for the curve into that and trying to differentiate. So this is much cleaner, in my opinion. We also need the velocity vector when t equals 0. Let me do that here. And I think I can do this out loud. So the derivative of cosine is negative sine. Evaluate that at 0, you get 0. Derivative of sine is cosine. Cosine of 0 is 1. And then for t squared, that's 2t. But if t is 0, that's 0. So actually, I will now tell you the rate of change of f along r at the moment when t equals 0 right here. So we'll do the dot product. It's the dot product of this vector and that vector. That's going to be 0. Okay, so in my opinion, this was the nicest way to get to the rate of change of f along r at this moment. If you wanted to avoid the chain rule in this problem, what you would need to do is compose the functions as they're given. So you would plug cosine of t in for x, sine of t in for y, and t squared in for z to get to a function of one variable. And then you would differentiate with respect to t, and then you would plug in 0. In my opinion, this process was more pleasant. Let me give you a moment to repeat this when t equals pi. You won't get quite the same amount of zeros here. We'll have a slightly different answer. I believe the answer will be non-zero. But see if you can go ahead and work through this when t is pi. You do not need to do this line again. So the gradient of f we've already done. What you need to update is the position when t equals pi, the velocity when t equals pi, and then evaluating the gradient at our new position. Let's see if we get to the same answer. So what is the position when t equals pi? Cosine of pi is -1, sine of pi is 0, and then we have pi squared. What about the velocity at pi? The first coordinate would be negative sine of pi, that's 0. Then cosine of pi, that's -1, and then 2 pi. I'm going to take the dot product of whatever vector I'm about to write down and this vector. Since this first coordinate is 0, I'm going to save myself a little bit of time and just say that it doesn't matter what this is because in the dot product it's going to pair up with 0. So just a little shortcut. Okay, that's great because we could skip this. 3y squared is 3 times 0 squared, so that's 0. And then x sine xz would be -1 times sine of negative pi squared. -1 sine negative pi squared. Sine is odd symmetric, which means sine of negative pi squared is negative sine of pi squared. So I can do this. Okay, we can do this dot product now. It's whatever that first coordinate was, doesn't really matter. 0 sine of pi squared dotted with this one, so 0, -1, 2 pi. So we have 0, 0, 2 pi sine of pi squared. Okay, so I hope that you also got to the same rate of change for f at that point. This wraps up this discussion of the chain rule, but as I mentioned earlier, I have a separate video where I prove the chain rule in detail. I would also like to spend more time talking about gradients for scalar valued functions. So that's a topic that we will explore in future videos. Thank you for your attention.